Hey, welcome to the course. I hope the lab session last week was okay. There's one more this week. Hopefully next week we have the midterm. So I'm still figuring out a date where everybody can come. So today we're going to write code. So the midterm was only until the material to last week. And so today's material does not count for the midterm, but it's still, if you understand today's material, it will actually help you for the midterm. Because today we're going to write code using our model, and we're going to work on specifications. So we're really going to dive into real distributed algorithms, and we're going to also go from P to eventually P, like I said. So we're going to both perfect and eventually perfect. So you're really going to get a good start on really making distributed algorithms that work on real systems. And broadcast is an important primitive. So we start with broadcast. And what I'm going to talk about first is specification, how to say exactly what we want, and then I will implement all of these. And so this is best effort broadcast, reliable broadcast, uniform reliable broadcast. So there's this concept of uniform that I will introduce today. So many distributed algorithms have a regular version and a uniform version. So that's kind of special. Uniform is about failed nodes, so I'll explain what that means. And then we'll show the code. And for all of these, especially these two, best effort is the naive one, but for reliable and uniform reliable, we're going to show the code both for perfect and eventually perfect. And you'll see how it's interesting, how eventually perfect means you have to think in a certain way. Okay? A uniform also, you have to think in a certain way. Okay, so let's start. So here is the beginning, broadcast. How do you write broadcast from P1 to the other nodes? You make a loop that sends messages to all the other ones. Okay, P1 does broadcast of a message, but P1 crashes here. So it's not able to deliver all the messages. So in this case, it only delivers to P2 and P4, and somehow, because of the crash, it's not able to deliver to P3, and P3 is correct. So that's not very nice, okay? We want an algorithm that also works nicely when there's failures. Here we have failures, it's kind of messy. You don't know who gets it, huh? We don't know which one got it. So we want something nicer. So we can actually make lots of nice versions, and there's a huge number of versions. So you can see here 5 more powerful, successively more powerful versions. So the naive one is called best effort. Best effort, it's not really the best now. If I write a better algorithm, it's better. But best effort means the simple naive algorithm. So only if the sender is correct, messages are going to get there. So if the sender crashes, who knows what happens? Okay, so can we do better than that? So we're going to write algorithms that do better than this. And the first one is called reliable broadcast. So this one will actually allow the message to go everywhere, even if the sender crashes. So if you're sending a message and the sender crashes, you don't care. Everyone will get it. Or nobody, yeah? If the sender crashes too quickly, then we can't guarantee that. So it's actually all or none. Okay? They all get it, or nobody gets it. That means if you get the message, you as one of the nodes, you know that all the correct nodes have got it. Okay? But if you don't, then you know that nobody got it. So that's really nice. It's a strong guarantee. Okay? So that's the first one we're going to talk about. Then we can make it even stronger. the version uniform reliable broadcast is an even stronger one, and it means that, let's say you get the broadcast, but then you crash. But you still got it before you crashed. Okay? Uniform worries about the nodes that crash after they get the message. Okay? Whereas reliable, it only worries about the correct nodes, the ones that don't crash at all. But if you get the message and then you crash, uniform will guarantee that all the correct nodes got it. Also in that case. So it also worries about failed nodes. So that's a little bit tricky, but we'll explain it more in detail. And then there's ordering, FIFO and causal. So these I'm not going to talk about today, but FIFO means that if I send two messages to node 2, they will arrive in that order. 1, 2. They won't switch orders. Okay, even if one of them is slow or not. First in, first out. And that's a first step towards causality. Causality is the strongest ordering one, huh? Whereas you also have the transitive relation. So if two messages have some causal connection, if one happens before the other, then they will also be delivered in that order. Even if it's because of some weird connection, they will be delivered in causal order. So this is harder, okay? This means more code, okay? And still handling failure and uniform and everything, huh? So today I'm going to talk about these two, reliable and uniform reliable. So you'll know all about reliable and uniform reliable. So we're going to do it in 2 steps. First I'm going to specify them, because for distributed algorithms it changes a lot. Small things can change a lot. It can even make it impossible, huh? If the system is asynchronous. So that means specifying is very important. Okay? So we're going to specify them first, and then I'll show you the code. And we'll play around with the code. Okay? So the simplest one is the best effort. So it has 2 events, best effort broadcast and deliver, and it has 3 properties. So you can start now getting the idea how we're going to define algorithms. Huh? There's the events, so the request going in, the indication going out, and then there's some properties, which could be safety or liveness properties. Huh? So here there's going to be 3 properties. So the intuition is very simple. Everything works if the sender does not crash. Okay, so maybe you think that's fine, you know, it's enough for me. As long as the sender does not crash, everything's fine. That's the intuition for this one. So there's 3 properties that define it perfectly together when you take them together. Validity, if PI and PJ are correct, then any broadcast by PI is eventually delivered by PJ. Okay, so if they're both correct, then we're good. Okay, and then there's more properties to make sure that the algorithm doesn't do too much. Okay, so no duplication, no message delivered more than once, and no creation. No message delivered unless it was actually broadcast. Okay, so these 3 together define the best effort. So you see how we do it. We have the basic functionality, and then we have some extra properties to make sure that it's doing exactly what we want. Okay, you see that, right? And now you can. The question is, which one of these are safety and liveness? So that's exercise for you. Okay, you can do that exercise. So here's an example. So I have P1 is broadcasting, and when I make a line going all the way to the end, that means the node is correct. It doesn't crash. And P2 delivers. P3 does not get it. Somehow it's not delivered. And P4 delivers. Now the question for you is this allowed for the specification of best effort broadcast? So remember the intuition. Let me just go quickly. The intuition and the formal definition. Huh? Everything perfect unless the sender crashes. And then these are the properties that define that. Huh? So is this allowed? So now you tell me, yes?
Do we consider there is nothing after?
The algorithm is done here. So all these in this example, all these nodes are correct. If I don't put a red X on this, then the node is correct in this notation.
Yes, can the P1 send a message after?
No, the algorithm is done here.
Okay.
It's finished. This is a complete execution of the algorithm, and from this diagram you can tell whether the nodes are correct or not. Huh? So in this case, all the nodes are correct. Huh? And anything wrong that happens will be denoted with a red X. So in this case, P2 and P4 are delivering the message, but P1 and P3 are not. Huh? So is this allowed according to the formal specification? No, why not?
Because the message has to be delivered.
It has to be delivered
Eventually.
Eventually? Where?
Because P hasn't crashed.
Because P1 has not crashed.
So P2, P3 must.
And the others have not crashed either. Right? Right? You're getting it, huh? So the best effort means that if the sender does not crash, it delivers to all correct nodes. So they're all correct here. That means all of them should deliver here, okay? They're all correct. They should all deliver, right? Huh? So this is actually not satisfying this specification. Huh? So I'm going to give you lots of little things like that in today's lecture. I'm going to show you something, and then I'm going to ask you, is that allowed or not? So is this allowed? This is not allowed. Huh? Because in the best effort, if the sender is correct, then everything is good. That means all correct nodes are going to deliver. But here we have two correct nodes that are not delivering. So that's not good. That's not good, huh? That's not allowed. Okay? Right? You see that, huh?
You want to deliver also?
Or to itself, yes. All the nodes. When I do a broadcast to n nodes, yeah, I also have to deliver to itself. Absolutely. It has to deliver to all nodes. Huh? So this is bad. And one of the reasons is that P3 is not getting it, but P1 is not getting it either. So here's a small variation. Here we have basically the same pattern of messages as before, in the previous one. See, same, except that now P1, it's running and boom, P1 crashes. So in this case, P1 is not correct. So is this satisfying the specification of best effort? Yes or no? Someone else. If you say yes, you have to say why.
Yes.
Why?
Because the sender crashed.
So, and what does that mean? The sender crashed, yes?
And we will never know what happened.
So you never know. So in fact, yes, that's exactly it. If the sender crashes, anything is possible, okay? So anything is possible. And if the sender is correct, then everything has to be good. But if the sender crashes, then, and you can see that from the, here, if Pi and Pj are correct, so if there's an if-then, so here's a general rule of thumb. If there's an if-then, if the if condition is false, then this says nothing at all. So if Pi crashes, this if condition is false, that means this condition is not saying anything at all. Okay? Whenever there's an if-then condition, you always have to look and see what makes the if condition false. And that, if that happens, then that if-then is saying nothing. Huh? So in this case, this is allowed, because P1 crashes. So that means that the first property is actually saying nothing. It's putting no constraint on what is allowed. So anything can happen, in fact. Huh? Well, satisfying, you can look at the other two properties, of course, huh? But in any case here, this is not satisfying a best effort. Okay? So this is kind of a not so nice algorithm, because we are worrying about systems where nodes can fail, and it has to work even if the nodes fail. So how can we make it better? Okay? So the point is, we want to make this naive algorithm better, huh? So best effort gives no guarantees if the sender crashes. You see that, huh? So how do we make it better? We can make it stronger. We want to give guarantees, even if the sender crashes. So we want the thing to work, even if you have failures. Now that's the general idea of a distributed system with partial failure. It has to keep working, even if nodes crash. Okay? So that gives us reliable broadcast. So that's a stronger version. So we add a new thing in blue here. If the sender crashes, we still want to give a guarantee. Well, the idea is all or none of the correct nodes will get the message. That means if at least one gets it, then they will all get it. Of course, it's possible that the sender crashes really, really quickly, so it's not even able to send one message. Okay, that's possible. So that would be the none case. Huh? But if at least one message gets out, escapes, before the sender crashes, then we know all the nodes are going to get it, for sure. Guaranteed for this algorithm. Okay? That's a very nice guarantee. Huh? So if I'm one of the nodes, now I get a message, then I know that all the other correct nodes also have gotten it. So I know that for sure. That's very strong, huh? Best effort, I wouldn't know, yeah?
When you say if I get, then all the time the other really gets. So you don't know actually.
When the algorithm terminates, but you know it will eventually terminate. So if you have some, yeah, so for all the algorithms we talked about, the algorithm at some point it's done. Okay, but we don't know exactly how much time it's going to take. But we know that after some finite time, it will be done. So if you want to determine what is that time, we're not going to talk about that. You need extra information like how fast is your network, or how fast are your computers, okay? Or are there really nasty routers in between? So, but then you know that in the internet, you can sort of set approximate bounds. So in this specification, all we are saying is that eventually it will be done. If you want to know the exact time, you have to do extra reasoning. We're not talking about that here. But you're in a good place because you know it will be eventually finished. Huh? And you know how fast your network is. Huh? So usually you can actually put a pretty good, you can make a pretty good cutoff on that in practice. But in this reasoning, it's only, we know eventually. Eventually means finite time. That's a pretty good thing. Huh? So all or none. So when the algorithm is done, it will be all or none. That's very nice, and it's much better than best effort. Huh? So we're going to write the code for this. But can you imagine, how do we actually get this? It's kind of magical, right? Yeah?
If one node gets the message, it will broadcast?
It can broadcast. So the nodes actually do some of the work. Yeah, so that's the point. So the way this is going to work is that any node that gets the message, it's going to actually forward the message on. Huh? So that's the idea. So you see, it's not that complicated, the idea. So now we're going to make the specification of reliable broadcast. So again, events and properties. Okay, it's always going to be like that. Huh? So request indication, RB broadcast, and RB deliver. So again, broadcast going down, request going down, and deliver coming up. Now we have 4 properties. RB1 through RB4. So we're going to keep all the best effort properties. So validity, If PI and PJ are correct, then PI and PJ will get it, okay? But we're going to add something more. So no duplication, no creation, we keep that. But we add an extra thing. So RB does something more. So it does everything that best effort does, but it does more. You see that every RB execution will be a correct BEB execution, huh? Because these three properties are holding. But not inversely, yeah? BEB can do messy stuff, but RB will not do messy stuff, huh? So the fourth one is, if a correct node delivers M, then every correct node delivers M. If one correct node, any correct node, actually gets the broadcasted message M, and correctly and delivers it upwards, then we know that every correct node. So that's the specification. So we have to implement that. Of course, you can say, is this going to be safety or liveness? I leave that up to you. Whenever we have properties like this, there's going to be safety and liveness properties. So nice exercise, of course, is to see which ones are safety and liveness. So I'm not going to go into that now. I'm just telling you that it's a good way to understand better what it means. Okay, so RB4. Okay, now we can do what I call specification engineering. We added this extra fourth property, but we can actually polish a little bit the specification. It's nice to tweak it to make it simpler. Okay, so this is our original specification. So remember, if PI and PJ are correct, then any broadcast by PI is eventually delivered by PJ. And now we've added this fourth one. If a correct node delivers M, then every correct node, and we have the two middle ones too. We can actually simplify this one now because of this one. We can take these two and we can make a little bit of a tweak. So that's kind of a nice thing to do, make specification a little bit simpler. Okay? So we can replace RB1 by a simpler version. And together, 1 and 4 will be equivalent to 1 and 4 before. So we have not changed anything here. It's just that it's a little bit nicer, simpler, easier to check it out. So here we have two nodes in the if condition. That's kind of complicated. It would be nice to have only one node in there. Okay, you see, here we have two. So we can actually say if any correct PI broadcasts M, then PI itself will eventually deliver. So if you combine this with 4, you know that all the correct nodes will get it. You can see that it's equivalent to this one. If you combine it with 4. So 1 and 4 after is this equivalent to 1 and 4 before. That means it's if and only if. But this one's nicer because you only have one PI in the if condition, which is much more comfortable when you want to reason about it, okay? So you get that, right? Because now I'm going to show you some scenarios. You have now, you see how it works, If any correct node PI broadcasts, it will itself deliver. And if any correct node delivers, all correct nodes. So you get that, Okay, we will see if you get that. Here's a possibility. P1 broadcasts M and then crashes, and nobody else gets it. 2, 3, and 4, all of them are correct, but none of them gets it. Is this okay? Is this allowed? What do you think? Is it satisfying the previous? Remember for the if condition?
Yes.
Yes? Why?
Because no one got it.
You have to say more than that. No one get it. Yeah, I see that.
No one
see that,
delivers and the sender is crashed. So
okay. Well, we can actually take a look back. So here we have if a correct node, and here we have if a correct node delivers. So here we have if a correct node broadcasts. but no correct node is broadcasting. Here we have if a correct node delivers, but no correct node is delivering. So those two conditions are vacuous. So yes, indeed, you see that? The conditions are not constraining us. So that is a correct, reliable broadcast. It's kind of a worst case, huh? But at least it's consistent. If P2 doesn't get anything, then P2 can say, I am sure that nobody else got anything either. So they're all in it together, huh? So, right? So that seems reasonable, huh? So here's another one. Slightly different. P1 broadcasts again and then crashes. 2 and 3 are correct, but they get nothing. P4 actually, it delivers, and then it crashes after. So this crash is before the end of the algorithm, huh? So this mode, P4, is not considered as correct, huh? Is this allowed or not? What do you think?
Yes.
Yes? Why?
Okay, because no correct node broadcasted and no correct node delivered.
Yes, yes, that's right. It's the same as before. Yes, indeed, you are correct. This is a correct execution. And to give a little more intuition, crashed nodes don't make any difference here. The fact that P4 delivers and then crashes doesn't make any difference because reliable broadcast doesn't worry about crashed nodes. We're only worrying about the correct nodes here. Huh? So this is okay. Okay. What about now small variation again? Now P1 again broadcasts, but now P1 does not crash. But P4 still delivers and then crashes. Is this a correct, reliable broadcast? And someone else, I know there's a few smart guys who will understand, but what about the others? Yeah?
No, it's not allowed because P1 P1 doesn't deliver itself.
Doesn't deliver to itself. For P1 is correct, and the first condition says a correct node, when it broadcasts, it must deliver to itself. And it's not doing that. No deliver here. So this is an incorrect reliable broadcast. It's still a nothing where nobody gets it, huh? But in this case, there's a liveness problem. It's not good enough, huh? You could say it's still doing all or nothing here. It's just doing nothing. Yeah, but that's not good enough. Sometimes it has to do all. And the conditions say it has to do all in a lot of cases. So this is a case where it should do all, but it's doing none. Okay? So this is not good enough for a reliable broadcast. Okay? Okay? Okay, one more example. Slight variation. So here P1 is correct, P2 is correct, P4 is correct, P3 is crashing. P1 will broadcast, it delivers to P1, it delivers to P2, and it delivers to P4. But it does not deliver to P3. Is this a correct, reliable broadcast?
Yes.
Yes? Why?
We do not care about crashed nodes.
You don't care about crash nodes, so we don't worry about P3. And what about the others?
Correct nodes delivers all other correct nodes. So.
Yeah, so P1 delivers to itself, that's correct. And all the other correct nodes, they also get it. So we're fine here. This is a correct, reliable broadcast. Huh? Okay, this is good. So you see what, now you see what it's getting, you're getting from this. Failures make it a little bit tricky, but not that tricky. Huh? Basically, you worry about the correct nodes here. Huh? Okay, so that's reliable broadcast. Okay, now, once you got this in your minds, I want to make it even stronger now. Now I'm going to talk about this version, uniform. Okay, uniform. There's many distributed algorithms that have a regular version and a uniform version. Okay? So uniform means I worry about failed nodes. So what does that mean exactly? You know that regular reliable broadcast doesn't worry about failed nodes. The node fails, I don't care what it doesn't count. Okay? But the uniform will worry. So the next point is we're going to make it even stronger, the reliable broadcast. We're going to say something also about failed nodes. Okay, so I'm gonna try to give you a lot of intuition on this, huh? So first of all, why is it called uniform? Well, again, it's a leftover from the 1990s, this adjective. But here it's kind of intuitive. Uniform means that the correct and the failed nodes are handled approximately in the same way. They're worth as much. So it's uniformly going to handle correct and failure. Huh? So correct and failed nodes will be, it tries to handle them in the same level. So that's what it means, intuitively. But what does it mean precisely? Okay. Now here, I want to give you a real-world scenario. Okay. So uniform is important when the algorithm is actually doing something in the real world. Let's say the broadcast is a command from some general to launch a nuclear missile. Okay. Aha. Now that's kind of dangerous. So it's kind of important to know if the missile was actually launched or not. Even if not, I mean, it's a war situation, nodes are failing, there are missile silos and headquarters of the army all over the place. They're all the nodes, and they're failing because bombs are dropping and so on. And the general says, launch this missile. Did the missile actually get launched? Okay, now let's say the broadcast goes to the missile silo, and then a bomb drops, and the missile silo is destroyed. So it's like a failed node, the missile silo. It's a failed node. But did it launch the missile or not? I mean, it could have launched the missile just before it got destroyed, right? It could have. The reliable broadcast will not tell me that. But uniform will tell me. Uniform says, if a failed node delivers, if it delivers and then crashes later, then all the correct nodes will get it. Okay? That means if the missile was successfully launched, okay, and then the silo crashed, then all the correct nodes will get acknowledgement that it was launched. And this is not something that reliable will do, because reliable, if it fails, we don't know anything. Okay? So the general does that, and then the general runs this uniform reliable broadcast algorithm, and he gets a delivery. Well, then he knows that the silo that was destroyed, it could have gotten a delivery. It's not guaranteed, but it could have, because maybe there's another silo, and it went to that other one. So, but it knows that, the general knows that it's possible that a silo has launched a missile. Whereas if he does not get the message, okay, then he knows that nobody got it. Okay, so this is a kind of intuition of it. Huh? So the uniform, if a failed node delivers, then all the correct nodes deliver. Huh? It might be that there's other failed nodes, and maybe they failed before we can do anything. So you can't really make everybody deliver, but you can make all the correct nodes deliver. Okay? So if a failed node delivers, all the correct nodes will deliver. For sure. So that's stronger than reliable, because reliable doesn't care about failed nodes, huh? But this is actually a much trickier algorithm. This is much harder to do than a regular reliable broadcast, huh? But let's give the properties and then the scenario. The property is actually very simple. It looks almost the same as reliable, in fact. So here's uniform reliable. So here it's URB broadcast, URB deliver. It has 4 properties, URB 1 to 4. Okay. The first 3 properties are the same as reliable and the same as best effort. But then there's this 4th one, agreement. But this is called uniform agreement. If a process delivers M, then every process delivers N. So this is slightly different from the reliable one. There's one adjective missing here, which is correct. So in the reliable broadcast is if a correct process delivers M, then every correct process delivers M. Whereas here, if any process, including failed ones, so if it delivers and then crashes, it delivered. Okay. It actually delivered. If that happens, then all the correct processes deliver M. So this is actually a very strong thing. We remove this adjective. You see that? Now we're worrying about failed processes. And actually, it's much harder algorithm to implement. Small change in the specification, and you'll see it makes a huge difference in the code. Okay? So yeah, one to dead and alive. So here we're worried about alive nodes, but also the failed nodes. If any failed node delivers, then all the correct ones must deliver in this algorithm. They will deliver if it's a correct implementation. Okay? Okay. So now we're going to start implementing them, and then you'll see how it all turns into real code. And the real code will give a lot of intuition on how it's really working. Okay. Okay, first one is best effort. But I'm not going to waste much time on best effort. So we're going to use the perfect channel. Remember we saw this perfect channel that when you send a message it receives exactly once the message. Okay, so we're going to use that, and we're going to have a simple for loop to send messages. For P element of all the nodes, set of all the nodes, send it. That's it. And each node will receive and deliver. So that is totally trivial code. So it's really the simplest code. You can see it's actually built on top of fair loss. Remember, we built perfect channel on top of fair loss. So the actual thing that the internet is providing us is fair loss. And we build this thing, which is a very naive loop. That's the simplest, totally simplest one. We can actually prove that this one will satisfy best effort. If the sender does not crash, every other correct node will receive the message. Fine. And also the sender will receive it. And the no creation and no duplication comes from the perfect channels. Remember, they will not create and duplicate. Okay? So that's trivial. There's no work really there. The work is when you start wanting to do the reliable one. Okay? So let me do a couple of algorithms. So we're going to do a few algorithms. So the first one is called lazy reliable broadcast. And lazy basically means that it relies on this perfect failure detector. Okay? So this algorithm actually needs P. It needs a perfect one, okay? So how do we do it? So the broadcast is very simple. We just do a best effort broadcast. Okay? And then the node that does the broadcast will get the deliver itself, and then it does an RB deliver. It's a layered thing, right? So we have the best effort broadcast. So the lazy reliable is built on top. It's a layered thing. Remember, we're always building layers. So we're getting this. So when I do a lazy reliable broadcast, I will do a best effort broadcast. Eventually there will be a best effort deliver coming up, and then I do a lazy deliver. Okay? You have to be not confused between best effort deliver and reliable deliverer. Those two are different, huh? BEB deliver means this message, huh? And reliable deliver means this one, huh? So what the actual application wants is RB, huh? Whereas BEB is just part of the implementation, huh? All of this is part of the implementation, huh? Okay? Okay. If the sender crashes, so this is the trick. If the sender crashes, the other nodes will see that because of the perfect failure detector. So, for example, another node will get the message M from the sender. It will then detect the crash. That's the perfect failure detector. And once it detects the crash, it will itself do a best effort. It will redistribute M. Okay? There's another possibility that another node will detect that the sender crashes, and then it gets the message M from S, from this crashed node, and then it does the best effort broadcast. Okay? So, little question for you. What's going on here? I detect the crash, but after I detect the crash, I get the message. Is that even possible? What's going on here? So it is possible, huh? That's possible. Why is it possible?
Network latency?
Network latency, absolutely. So the crash might be somehow a very fast message, but the message traveling in the network, it might be slow. There's no guarantee on message travel time, okay? So it's like you're getting a message from a crashed node, but this message was already in the network when the node crashed, huh? It's just you got it slower. So that's possible, huh? So you have two possibilities, and you have to handle the two. So the reason why the code is a little bit complicated, it's actually 2 slides. Ooh. It's because of these 2 cases, actually, huh? You have to do a little bit more work, because we have to handle both of these. Okay? So now we can start writing code on this. Okay? We also have to filter duplicate messages. It's possible that the same message arrives more than once at a node, because there could be 2 other nodes detecting that the sender crashes. They both do best effort, or maybe they don't. Maybe one is very fast, it does the best effort. The other one is slow, it doesn't have to. But maybe they both do it, so this other node will get the message twice. So you have to worry about that too. Okay? So that can happen. Yeah?
Can we just repeat why case 2?
Why case 2? Well, so the sender does best effort broadcast, and some other node gets that message. So typically the node will get the message, and then later on it will detect that the sender has crashed. Okay? So it's 2 messages. One of the messages is M, and the other one is information from the failure detector. Huh? But this is also possible. I can detect the crash before I get the message. First I detect the crash, I detect that the sender has crashed, and then later I get a message from the sender. It's like the ghost of the sender has sent me a message or something, right? Now how can the crashed sender send me a message? Well, because of the delay. Maybe this failure detector, for some reason the messages were going fast, but the message was already sent, of course, before it crashed. Huh? See that? There's no guarantee that the messages arrive in the same order they're sent. Huh? The delays could be anything, so it has to work. So that makes the algorithm more complicated. Huh? And in real networks, it's like that. Huh? Even if most of the time the order is kept, sometimes you get a little bit of congestion and it slows down the message, and the order is flipped. So even in real networks, maybe case 2 is rare, but it happens, huh? So the model, we have to model it, huh? If we want a correct algorithm. So that's the idea. You see the intuition? So now we write code for this. Okay? So I'm going to show you the code of reliable broadcast, and it uses 2 modules. So basically, there's also this perfect failure detector here. There's 2 modules, which is also sending messages up, huh? So there's 2 underlying modules on top of, underneath this one, huh? And then we have a bunch of local variables, which I'm going to initialize here. You'll see what they do. So delivered is basically for removing duplicates. These are all the delivered messages. It's empty set, star. Correct is all the nodes that have crashed. So capital Pi is just a set of all the node names, P1 through PM. Huh? So whenever I do pi, it'll be P1 to Pn. Huh? So I start by assuming all nodes are correct. But this correct variable will get smaller and smaller as the execution goes on. Delivered will get bigger and bigger as messages are delivered. And then we have this set from PI. We have to know messages coming from. So we'll see what we use this one for. So this is an array of sets indexed by the name of the node. So we know things that are coming from PI. Okay? So it starts by being empty. They're all empty. For all PI elements of big pi, it's empty set. Okay? So this is keeping track of the messages coming, indexed by the name of the node. So you see it's very nice pseudocode. Huh? I'm assuming this very sophisticated data structure, very easy. Okay? Okay. Now the algorithm starts. I do an RB broadcast, so that's the upper thing, RB broadcast. What it does, it just does a BEB broadcast underneath. That's all it does, okay? So basically, so yeah, filtering duplicates, save messages, and now we start looking at the second page of the code. So there's 2 possibilities for a node. Huh? It can either get a crash message, or it can get best effort deliver message. Huh? So what if a node, any node, gets a crash message? So the failure detector can tell it at any time. Maybe P3 has crashed, okay? So what do? First of all, you remove the node, PI, from the correct set. So the correct set will always be going smaller and smaller. Huh? And now we have to handle the case. Remember case 1 and case 2? So case 1 was when we got the message, okay? And the crash came after. So that's case 1. So we got the message, and the crash message came after. Whereas case 2, it's the other direction. Okay? So case 1, we have to keep track. If PI has failed, did we get any messages from PI? Well, if we did, we have to re-broadcast them, like we were saying before. This node has to do the work of the sender then. So that's what it does. It does a best effort broadcast for each of the messages that came from PI. So that's why we need this array from PI. Okay? And then we have a more complicated piece of code, and that's it. That's the whole code, but this is the most complicated one. So if the node gets a best effort deliver, so first of all, there's an if. If the message is already delivered, we don't do anything. We only do this the first time we get a new message. Yeah?
What is data?
Data is just some label. It's just some label because we're sending like a record. So the best effort broadcast, you can send any kind of a package. So we're not just sending a message. down here. We're sending message plus more information in some sense. Whereas the reliable broadcast will just send a message. Actually here, we're actually sending more stuff. Okay, we're not just sending M in the BEB, we're sending M plus the node it comes from. So we just kind of make this look like some kind of a record. The data consists of SM and M. So it's like but the best effort broadcast algorithm doesn't care. This is for this algorithm, this is just like a message, but the real message is inside there, and there's more information. See, so we're kind of using it generically, this best effort. We're sending more information. That's okay. We're allowed to do that, yeah?
So the SM is the information about the message?
Yeah, the SM is where the message originally came from. So this is a pair. So this from of PI, it actually gives you all of the messages that came from PI, but SM is the original node it came from. Because when you do get a message, you have to know what was the original sender. So it's like the original sender, okay? Because otherwise, it has to be like as if it was the sender sending it to you. Okay, so all of that is just a little bit of bookkeeping, I mean, you could change it and the algorithm would be a little bit different, but it's nice to keep track of that, So this is the crash, but the other case is when you actually get a delivery. Okay? Now, usually, so this we have handled here the case when we got the delivery before the crash. Here we do delivery, but we have to handle the case when the crash, when the crash actually happened before. So here, for example, we only do something when the message, the first time. So we have this if M is not delivered, and then we add M to the delivered set. So this guarantees that this stuff will only be executed once for every message. Guarantee, only once. We add MSM to the from set, because that's where, because this message actually, it came from PI, okay? And then we do an RB deliver, okay? This is reasonable because the message has arrived at this node, okay? And so you do an RB deliver the first time only, And then you have this little condition at the end. If PI is not correct, what that means is that the crash message actually was already handled before. Okay? So if PI is not correct, that means we've already done this before. Then we do a best effort broadcast. You have to redistribute. So this is the, okay, this is the case 2. This is the case when the crash happens, it comes before the BEB deliverer, and the deliverer is slow. The case when it's like a delivery from a zombie, but it's not a delivery from a zombie, yeah? So you see that the crash handles the first case, and the BEB deliver handles the second case. So you see, this code, it looks like there's a lot there, but each piece, it means something, It has its purpose, And we have to handle the two orders. We have to keep track of delivered message. We have to keep track of the messages in order to redistribute them. And if we get a message, we have to broadcast it here, either here or here directly, But if we find out here that the message crashed, then we don't know what the message is, So that's why we need this from thing, because otherwise this crash piece of code will not know what are the messages. We have to keep track of them inside the from. Okay? So that's it. That's the whole code. Yeah?
This means we have to keep track of every message we received since the...
Yeah, this is not very optimal algorithm, But it has a great advantage. It's correct. Okay? See, this is the first thing. Yeah, this is not the optimal algorithm. So if you want to turn this into a real practical algorithm, you have to do a little bit of garbage collection of these data structures, huh? But that's normally that's kind of easy. You can find out as soon as everybody has as soon as the message M has been delivered by everybody, then you can remove all the data related to M. So I don't show that here, because that would make the code more complicated. I first want to show you a correct algorithm. This is already not so simple algorithm, huh? This is N nodes, so it's already concurrent. They're all running in parallel. Each node can have RB broadcasts coming in at any time, completely concurrent, and nodes can crash at any time. This is an extremely concurrent algorithm, huh? And it handles partial failure. So correctness is by far the most important thing. But you are absolutely correct in the sense if you want to make this practical, you have to do a little bit of garbage collection after. But that doesn't have to be so efficient, huh? You can allow these things sort of to grow for a while, and then at some point you figure out that everything related to M is done, so then you can clean them up. Okay? So it's not so critical. You can allow them to grow a bit, and like every 10 minutes or whatever, you do some kind of a cleanup. Huh? Or you do something smarter like in TCP. You have like sequence numbers, or you have windows. I mean, there's ways to make it more efficient. But by far the most important thing is having a correct algorithm. Huh? But no, you're completely right. But it's important to have a correct one. You know, if it's not correct, it's over already. Huh? You can optimize all you want. If it's buggy, it stays buggy. Huh? So yeah, so that's completely correct. Okay, so this is the first really nice, juicy piece of code we saw. Huh? It's very nice, though, isn't it? It's 2 pages. This is like the most complicated kind of thing we're going to see. Huh? So this is like most of the code we're going to see will be 1 or 2 page. And that's it. Huh? And it's built on top of these other guys. Huh? So you can see for an algorithm that's both concurrent, parallel, and fault tolerant, the code is not that complicated, actually. Yeah? Right? This totally concurrent algorithm. I don't know if you have much experience with writing complicated concurrent algorithms. Usually there's more code than this, huh? And it's harder to prove them correct. This actually, the proof is going to be quite simple. Okay, let me make a small break now.